So we're going to talk about floating point arithmetic today, and I'm going to try to do this, I guess, in two installments. It's just a lot of slides to go through, and so in the first half, I will cover basically the representation of floating point numbers, and in the second half, I will move on to actual computations such as addition and multiplication and division and so on in this representation. So as we sort of like talked about this briefly, I guess, in one of our classes not too long ago, floating point representation, number representation is introduced in order to provide a broader range of values to our arithmetic operations, and these operations, of course, could always be conducted on integers, and they are in computers, but they're also used with these other numbers, which we call floating point numbers, where we could think of a floating point number as a number with a radix point. And that radix point, depending upon where it's located, kind of determines the values of the numbers that we're looking at. For example, when we put the radix point to the very left-hand side of the most significant digit in the representation, not counting 0, we get numbers from 1 over 16 to 15 over 16 if we assume a 4-bit representation. If we somehow move the radix point between the leftmost bit and the bit following it to the right, then our numbers become basically 1 over 8 through 1 plus 7 over 8. And then if you just keep doing this and then keep moving the radix point towards the right, ultimately you get to a place where the radix point, or in this case the binary point, stays or just is placed right to the right of the least significant bit, then you get nothing but integers. Now, if you continue to move the radix point or the binary point to the right, you will basically, every time you do that by one place, you're going to double the numbers inside the range of values that you have. Of course, in 4 bits, or with 4 bits, you cannot represent any number besides 16 distinct numbers. And these numbers can change. Like in this case, we represent numbers, even numbers like 2, 4, 6, 30, which basically doubles these numbers. And then if you just make it, if the binary point goes to the right one more place, then they're going to be basically 4, 8, 12, and so on. And 0 is always there. So the idea is to have that point somewhere, and that somewhere is critical in so far as how do we view these numbers. And so for that, we kind of resort to this scientific notation. And in this notation, we have a sign, bit, if you like, a mantissa, which is a p-digit number, sometimes called significand, a base, b, and an exponent, x sub u. So these 3 numbers, along with the sign bit, give us the floating point numbers that would obviously change with the values that we have here. B itself is called the base, and that's typically equal to 2. In modern computers, the base is chosen to be 2, even though in the earlier machines other bases were used, including the decimal base. So what happens here is that when we get a certain number of bits fixed to represent our numbers, we kind of divide it between the mantissa portion and the exponent portion of our representation. So as a result of which we have some precision to specify the fractional portion, if you like, of the number that we're interested in versus how far we can just move this number along the, let's say, x-axis, either to the left or to the right of 0. So the exponent gives us the range, that number which we call x sub u. And the mantissa gives us the precision, meaning how many bits we allocate to represent the fraction or the floating point mantissa. So if I set these numbers, for example, to p to 10 and k to 20 and b to 10, and here the k is the number of bits or digits in the exponent, and base being 10 in this case, the largest exponent we could really have with 20 digits will be 10 to the 20 minus 1. That's as far as we could actually push this exponent with 20 bits or 20 digits. And this, of course, number itself, that the exponent also represented in base 10, that is to say that being a decimal number, that's what gives us this 10 to the 20 minus 1 number here as the largest exponent. And of course, as the base is equal to 10, we then have to power this base to this largest exponent we can have to find the largest exponent that we could, I guess, the portion here, which we call the exponential portion, or the exponent portion, which is really both of these combined together. And of course, for the mantissa, when we set all of our digits to the highest possible value, which we can set here, and if we take our m to be also a base 10 number, a decimal number, then it'll be 1 minus 10 to the minus 10 with 10 decimal digits in the mantissa portion. That's again because we are looking at a fraction which is very close to 1, which really the only thing that makes it less than 1 is that everything is 0 between the decimal point and the last digit, which we have to set to 1, because if we make it also 0, we make that also a 0, then of course we'll get nothing but 0 here. So this is the minutest number which we can subtract from the largest number, which would be 1. If everything actually were to be 0, and then we had a 1 to the left of the decimal point, that would be 1. But now we want to subtract from that the minimum number, which we can write in a 10-digit mantissa. That would have to be all zeros, that is 9 zeros followed by a 1, which would then be equal to 10 to the minus 10. So that's with a negative sign. This is really the most negative number, because we've made this number as big as possible. So that's really become the most negative number, that being as big as possible, this being as big as possible. And on the other side, it's the same number with a plus sign, and again, this being the mantissa that can be as large as it can be made, times the exponent that can be made as large as we can make it. Then this gives us the maximum positive value, if you like, in this representation. Now, the least and most positive numbers would be, of course, the most positive numbers we already figured that would be this number. But the least positive number would be 1, where we still assume that the exponent, the sign is plus, of course. We assume that the exponent has to be minimum, and then the mantissa must be minimum. Of course, that would be minimum when we made all the digits from the first place to the ninth place 0, and then the last one equal to 1, which will then give you 10 to the minus 10. With the sign being positive. And then the exponent itself will be just 1 minus 10 to the, or minus 10 to the 20 plus 1, which is basically this number in reverse, in negative terms. And we're assuming that this is just coming out of this representation where xu can be a signed number with a plus and minus. And in this case, our assumption is that we're actually using a signed magnitude exponent, which would not be the case when we look at the binary version. And in the same way, the least and the most positive negative numbers will just have to be, these numbers with a negative sign in front of them. And of course, there's a negative sign here, which we haven't quite indicated, and which we have to place in there, right there. That makes it negative. And so those are the least and the most negative numbers that we could have. Again, the most negative number matches this, but the least one is this other number. So as I mentioned earlier, in nearly all modern processors, mantissa is a binary fraction, and the exponent is binary as well, x sub u, and base is equal to 2. Furthermore, this mantissa is normalized so that it is actually a number between 1 and 2. Not quite as large as 2, but very close to it. And so what that really means is that if we assume that the mantisses are expressed in signed magnitude notation, then they will always begin with a 1, followed by the binary point, as in this situation here, or as in this situation here. So the radix point is really placed between the most significant bit of the mantissa and the next most significant bit of it, the same way over here. And of course, what we also do is we make sure that the leftmost bit is always 1. That's what makes it between 1 and 2. As you can see that if I set all the remaining bits to 1, this number would always be something as close to 2, but never be, never equal to 2. It'll be very, very close to 2 as I put more and more ones into this sequence and increase its length. In a good number of representations, this leading 1 is actually not explicitly represented or placed into the representation, just to save that bit. It's not probably as important as it used to be in the past. Given that the memory is not much of an issue, this doesn't really have to be. If this still is maintained, that's out of the legacy of the systems that have been in place, so that this convention continues on. And so the hidden bit, that's what it is called, is always equal to 1, and it's not shown in the representation. So when you see a representation like this, the 1, the hidden bit, is not visible, and you have to sort of like assume that it is there. When you think about this as some kind of a binary string of values here, like 1s and 0s, from left to right, there is this hidden bit which is sitting right between the exponent and the mantissa, and that's equal to 1. And that means this 1 is just situated to the left of the radix point here. So whenever you take the string here, you just add to it plus 1 to make it so that you get the actual value of the mantissa. The exponent is biased, meaning that there is a true exponent, and that is derived from the biased exponent by this formula, which is basically biased by this amount here, 2 to the k minus 1 minus 1. So basically what this does, if you think about it this way, if you just write this in a way that x is equal to lowercase x plus this quantity, you're taking the actual exponent, which could really go between minus 2 to the k minus 1 and 2 to the k minus 1 minus 1, and then making it so that the most negative value becomes 0, and then the most positive value becomes the largest number you can represent in k bits. That would be 2 to the k minus 1. So the reason for this is that we want to identify the relative values of the exponent from the most negative to the most positive in a fashion that actually corresponds to their absolute, the absolute value of the representation, which is to say, when we bias the original exponent, the numbers that we write from the lowest to the highest represent the from most negative to the most positive exponents. Here's an example. So if you look at the biased exponent here, just pay attention to this column for a second, and look at the algebraic values. You notice that as an unsigned number, this is the lowest such number you can write, and this is the highest number you can write. And these are the algebraic values corresponding to these biased exponents. And you can see that the lowest exponent in the bias sort of sense is corresponds to the most negative exponent. And the highest exponent in the bias sense here corresponds to the highest algebraic exponent. That would not have been the case if, in fact, we took the original representation for the exponent, which would be effectively these numbers, and these are really two's complement representations, if you can see this. That's like 5 is equal to -3, 6 is equal to -2, and 7 is equal to -1. That's how you would have normally represented the algebraic values. So we really sort of like transition from the two's complement representation, and this would really have to be considered as -4, and that adds additional sort of confusion to this representation. But you can see that even though 6 is greater than 5, this is more, this is smaller in an algebraic sense than this is, and furthermore, so you can say that maybe like this follows a certain pattern, but all of a sudden you get to 0, and then this is where the inversion happens. Now you get 7 is -1 and 0 is 0, and 1, which is still smaller than 7, that's equal to 1. So this inversion is undesirable because sometimes, and often I should say, floating point numbers are compared for their values to see which one is greater. So if you think that the exponent is biased, and the mantises, of course, will be proportional to the actual values because they're assigned magnitude, then you can say that a number, a given floating point number A, is less than or equal to another floating point number B, let's say, if and only if, without the sign, that the exponent and the mantissa portions of the two numbers, when compared, provide that kind of an inequality. That is, the representation of A with the biased exponent cascaded with the mantissa is less than that of the biased exponent of B and the mantissa of B. So this is how typically you compare numbers that are floating point in floating point representation. You take X and XA and MA and think of them as one number. Just concatenate them, and take another number XB and MB, and then concatenate them, and then compare the two simply by subtracting, let's say, the first number from the second one. The difference will be positive if, in fact, this latter number is greater than the former number, that is, B is greater than A. And that would also be the way that these two numbers would relate to one another as floating point numbers. And because of the fact that the exponents, when in fact one's exponent is in a sign in a biased manner greater than the other one, for example, if in fact the mantises are identical, but the exponent of B is greater than the exponent of A, then clearly B is greater than A. That's how this table kind of helps us. which is to say, like if we were to have a number like 100 for the exponent of b, and then 010 for the exponent of a, we know for a fact that b is greater than a. And the mantises don't change this fact because they are kind of like their values will be will represent the relative values of a and b that would remain identical. This will not be an issue. It's just the issue of x, which is basically clarified or fixed simply by using this biased exponent instead of the original exponent representation, which is this middle column. Now let's just talk a little bit about the representation itself. Now there is this notion of a denormalized number, which I have to mention, and that means that when numbers are denormalized, that this hidden bit is assumed to be 0. That's the only time that we assume that. And that gives us the capability to represent mantises that are very small, because with this being a 1 all the time, we cannot represent very small mantises, leaving out the exponent portion of things. It will always have to be just 1 plus some mantissa here. And if we just nullify this, annul this to make it 0, then we can actually have a very small fraction. And so that's what it is basically. The denormalized numbers are the ones with which we identify the least exponent. So when the exponent has its least value, that is the most negative value, then we assume that the number is denormalized, the floating point number, and therefore we really have a 0 in the so-called hidden bit position. Now in this case we're looking at a 2-bit representation. So with 2 bits we really have 0, 0, 0, 1, 1, 0, and 1, 1. And the 0, 0 is the most negative biased exponent, that is, and that will have to be -1, which is sort of like with 2 bits this corresponds to -1 without these bits, and this corresponds to -2, and this becomes basically, I'm sorry, -1, 0, and then +1 here. Let's see, there are 4 values which we can write: 0, 0, 0, 1, 1, 0, 1, 1. So they would actually be -2, -1, 0, and +1 will be the exponents in this case. So when you have k equals to 2, the denormalized numbers that we shall write here with 2 zeros filling out the exponent portion simply gives us an exponent of -1, and that exponent would then be multiplied with, in this case, 0, because the mantis is entirely 0. And in this case, it will be multiplied by 1/4. That will make it 1/8. And then in this case, it will be 1/2 times 1/2. That will be 1/4. And in this case, it will be 3/4 multiplied by 1/2. And that gives you basically 3/8. So, and those are the values that you have. Now, when you look at the next exponent, that is the proper exponent, which is equal to 0, and I guess the exponent really ranges between -1 and 2. I should just stand corrected here, not -2, -1, 0, and 1, but it's actually -1, 0, and 1 and 2. That's how that goes. This is how we identify these values here. All right. So with that, we then have these remaining exponents. So when the exponent is 0, and this is how we write it here, then the number itself will have to be just 1, because that's basically 2 to the 0. And then that is just with a hidden bit of 1 here. Now it's no longer denormalized. It will be 1 times that 2 to the 0, which is equal to 1. In this situation, the fractional part is 1/4, and the number itself is fractional portion is 1/4, and the number itself is actually 1. So it's 5/4, which is 5/4. Okay. Basically, you add to this 1/4, and then of course to get to this, you add to this 1/2, 1 plus 1/2, and to get to this, you have to add to 1 3/4, which is what this number is. So I kind of go down the same way for the remaining bits, the remaining exponents, and the remaining patterns here. When you look at the negative numbers, the only thing that changes is the sign. Everything else will be the same. If you look at these numbers down this way, they're identical except for their sign. So the negative part is, straightforward once you work out how these are. So one more time, when k is equal to 2, the exponents run from -1 to +2. That just comes about because of the values that we have here. You just make the substitution. You have to make this substitution, of course, and you can see that that's going to have to come to basically, in this last case, you're going to have the exponent being 4 in the original case. That basically is what you're subtracting from the biased exponent. So it's like to get to the algebraic value of this so-called x. You can work it either way you like. You want to compute lowercase x, which is basically the capital X, which is 7 minus 3, which is equal to 4, the algebraic value-wise, and that's the binary representation of it. Or if you want to compute capital X from the lowercase x, then basically that is this plus 3, which is equal to 7. So that's how this formula works in this representation. In the case that we have only 2 bits, then the numbers really are from -1 to 2, as opposed to from -2 to +1. Not quite the 2's complement representation, but it is the biased exponent representation, which is slightly different. All right. So now that we said this, let's just mention a couple of things. And that will be something that would relate to the number of bits we could really allocate. Now, in this table, if you look at the table here, the last 2 rows correspond to IEEE 754 representations or standard formats. The first one is called the single precision. The second one is called the double precision representation. In the single precision, we got 32 bits. And we use 1 bit for the sign, and then 8 bits for the exponent, and then 23 bits for the mantissa. When we double the precision, then we use 64 bits, 1 bit of sign, 11 bits of exponent, and 52 bits of mantissa. You can see that these numbers are not equal to one another. We use a lot more mantissa bits than exponent bits because we want to have more precision than the range, you may actually say, because this, of course, is going to give us a big range. 2 raised to 2 to the 11 is more or less how big a number this is going to become if we just forget about the sign for a second. Now, these are the numbers that are going to be the sort of most positive and most negative values with and without a hidden bit. Without a hidden bit, of course, it'll be a fraction for the mantissa, but with the hidden bit, there will be a 1 plus this whole portion. That will make it 2 minus this. And as I said, that this is the exponent portion, which is 2 to the k minus 1, which you can take to be 2 to the 10 in the case of double precision. So you're talking about 2 raised to 1024, big number. And it's a very large number. If you think about a 64-bit machine in integer representation, that's 2 to the 64. This is 2 to the 1024. Basically a huge number compared to 2 to the 64. One thing that needs to be mentioned about the precision is that when you, for example, look at single precision representation with 23 bits, the smallest number you can actually have would be 1 over 2 to the 23. And no 2 numbers can be closer than this number, closer together than this number would be. And that number is like 1 point, all these digits, times 10 to the minus 7. In double precision, this difference actually reduces to something much smaller. You can see that this has become 10 to the minus 16. And so you would notice that both these numbers are actually integers. And that comes from the fact that you can think of this number as 1/2 raised to 52. And 1/2, you can think of that as like 10 over 5. I'm sorry, 5 over 10. 1/2 to the p is like 5 over 10 to the p. And so you can compute in decimal 5 to the p. And then to divide it by 10 to the p, all you have to do is to move the decimal point some p places to the left, is all you have to do. So you can think of this 5 to the p in base 10 as if we just take the log of this number in base 10, which is what this is, you get to know how many digits that this is going to have. So it's going to be p times log 10, log base 10, 5. And then you will divide this by 10 to the p by shifting, like I said, the decimal point p places to the right. Now here our p is equal to either 23 or 52. So we can compute this number here, and that will be the number of digits we're going to have in our representation, which comes out to be to 17 when p is equal to 23, and then to 37 when it's actually equal to 52. So if you go back here and count how many digits you have, like let's just count it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's the number we found out here. And if you count the other the number of digits in the second one, you're going to count exactly 37. I don't want to count it here because it's going to take some time, but you can verify this to yourself. So 37 digits, and then of course the rest of it is worked out by knowing that this would have been an integer with 37 in digits here, the number with 37 digits. So if you really moved the decimal point from here, which it was originally, that would have been essentially like 5 to the, this whole number would be basically all of these digits when this point goes over here is what you would have really gotten as 5 to the p, which is 5 to the 52. Now that number would not have had the decimal point here, but it would have had it over here. So basically what you did, you move this from this place to here, and that's about 36 places, because you have 37 digits here. So the number of places that you moved your digit is equal to 36. And that 36 is what you really have canceled from the 52, which this 10 to the 52 would have divided this original number. So basically you had this number which was like all these digits without the decimal point there times 10 to the 52, and then you made this number smaller. All the while you had to divide this by 10 to the 52, and then the difference was 36 places. So this is really, I should say this was 10 to the 36 because we just moved it over here. And that means you had to subtract 36 from 52, but since 52 is in the denominator, it would have come up to the numerator as a minus 16. So really all I'm saying is that you're dividing this 5 to the p by 10 to the p, and the way that you do that with 52 bits is simply by moving the decimal digit from here to this place 36 times, and therefore that gives you ultimately that ratio 10 to the minus 16, as opposed to 10 to the minus 52 that would have been if in fact you hadn't moved this from here to here. So same way you could do this with the p-value being equal to 23. In that case, of course, you're going to have, as we worked it out earlier, that was 17 digits. And this, of course, you have to do with respect to the number of mantis bits, which is equal to 23. Again, you move it 16 places, so that 23 and 7, or you can say, but this being moved only 22 places. That's how you get that number again in this situation. So the numbers work out just out of this ratio is basically all I want to emphasize, and that's really trivial enough to relate to. Now this is a little table that shows us how these numbers are represented. The most positive and most negative numbers are represented. Exponents have to be the same because these are the most positive and most negative numbers. And the only thing that really changes is the sign here. Everything else is the same. The mantises are identical. So when you compute these numbers, you get to have, in this representation, the largest in a single bit precision case, this 23 plus 8 plus 1 representation. And these are the numbers that you could really sort of like say most negative, most positive, most negative, and then least positive and least negative. These are denormalized when the exponents are set to 0. Signs, of course, are 0 and 1. And then the exponents, the mantises, are only going to have a single one in each of these strings. And the exponent 11181 pattern is used to represent what we call the extreme numbers, which are basically infinity, 0 over 0, infinity over infinity, 0 over infinity, infinity over 0, and so on. All these numbers that are typically a problem sum. And so you can think of basically in this representation format, the IEEE 754 format, the numbers basically having denormalized values and normalized values, and when you just fuse them together, you get what we call normalized plus denormalized numbers, as you can see here. And so the normalized numbers give us the small ones, and then the normalized ones with hidden bit give us everything else from that very end on each side to the rest of the range on each side. So extreme numbers really represent things that are basically sometimes exceptions, and sometimes they come out of the mathematics that are performed. And if these things exceed the representation's range, then we have to view those numbers as basically infinity in some sense, plus or negative infinity. And so many numbers would present an issue, as this slide explains, but because of that, you have to provide some means for mathematics to be conductible within a floating point representation, as floating point numbers represent more of the real numbers than anything else in the context of mathematics. Certainly come closer to real numbers than integers would ever come. And so in that regard, you have to make it so that it can kind of simulate the real numbers arithmetic as much as possible. So there are numbers that people give special names to. These are called not a number numbers, NaNs, and then quiet not a number numbers, and then the significant not a number numbers. And so like I said already, if you have a string of ones in the exponent, they really represent these so-called NaNs. And these numbers basically can be further differentiated by looking at their mantises. The mantises are essentially going to be set to 0 with the highest most exponent, if the number is infinity. If the mantis is not 0, but the exponent is still the maximum you can set it to, then it'll be actually what's called an NAN. And depending upon if it's a significant or a quiet NAN, then you either put a 1 or a 0 in the most significant bit pattern here. So here's a number which is a significant NAN, and here's a number which is a quiet NAN, which is a leading bit of 1. And you can see that if you set all the mantis bits to 0, they're plus and minus infinity. But anything other than all zeros would actually be with a leading bit of 0, significant, not a number. And anything with a leading bit of 1 in the mantis section would be considered to be a quiet, not a number. And of course, sign is taken into account as plus and then a minus. Now let's also talk a little bit about the approximation of real numbers by floating point numbers. And this becomes an issue because p itself is, no matter how big it is, it's going to be a finite number. Even though the larger the value of p, the smaller the distance, as we will call them in some metric, the difference between the two numbers, consecutive numbers, will become. And but there is a limit to this. That is to say, when we have a decimal fraction, which would include, let's say, some number like 2 to the minus s in its binary expansion. Every number can be expanded into a binary form. When s is greater than p, then we cannot represent that decimal fraction in p binary bits, and therefore that's not representable. Anything beyond 2 to the p minus p would be excluded from the representation. And so there's a whole bunch of numbers that cannot be represented in a p-bit representation, but it is actually somewhat more special than that, and this is what this discussion is going to lead us to. So what I've written here is a representation of a fraction that is having an exact representation in p-bits. And when this happens, we just write this as basically some fraction, which is going to be some binary bits that are divided by these powers of 2. That's how you write a binary, a decimal number as a binary fraction. Now, if you multiply both sides by 2 to the p, then you get 2 to the p equals 2 to the p times d equals this number. Now the number on the right hand side is clearly an integer because these bits are zeros and ones and everything else is a power of 2. That means this whole sum is an integer. Therefore this 2 to the p times d must be an integer. And that's what we figured out, that in fact if d has an exact representation, that 2 to the p times d must be an integer. Any other d would not fit into this representation. So if you take some d and multiply it by 2 to the p and don't get an integer, that means that d is not representable in this p-bit representation, and that's possible. Lots of numbers actually give you that condition. Now let's say that we make this a little more specific and then now look at d not in fact as some arbitrary number and without the number of digits left unspecified, or without specifying its digits, number of digits. Let's just actually make it specific and say, let us say that this d that we want to represent in p-bits is an r-digit decimal fraction. So when we look at it, we use exactly r digits to represent it. Like if it's 0.35, it means r is equal to 2. If it's 0.567, it is r equals 3. And now we want to represent this number, which is 0.567 or 0.35, as being a 2 or a 3-digit number in p-bits, and want to see if it has an exact representation. So now we already said that 2 to the p times d would be an integer. for this number to be representable in p digits or p bits. By the way, you can also show that r itself, the r we picked here, will have to be less than or equal to p. In other words, it takes more bits to represent a decimal number with r digits than r itself. That you would need more bits than the number of digits that a decimal number has in order to represent this. This is fairly obvious because that decimal representation is more compact than a binary representation, so more bits are needed. So with this inequality, we know that 2 to the p times d is an integer, and now we multiply it by 10 to the r and divide it by 10 to the r. And in the course of doing this arithmetic, we simply write this 2 to the p as 2 to the p minus r, because this is kind of equal to 2 times 5, and that is 2 to the r. That means 2 to the p divided by 2 to the r, and that's what this number is. And then what survives here is, of course, 5 to the r. And now this must be an integer. And of course, 5 is relatively prime to 2, so that means it cannot divide 2 to the p minus r. And we know that 5 to the r divides 10 to the r, and it kind of gives us 2 to the r. And when we multiply that by 2 to the p minus r, we get 2 to the r. And this, of course, 2 to the r times d now must be an integer, because there's no other way we can simplify this. The only simplification that we can put forth here is when we divide 10 to the r by 5 to the r. Or you can say that you divide d times 10 to the r by 5 to the r. And of course that is equal to 2 to the r times d. And this whole product becomes 2 to the r times d. And this must be an integer. Really, and I mean, like we're saying that d times 10 to the r divided by 5 to the r must be an integer, but that is 2 to the r times d. And that must be an integer. There's no other way that we could generate an integer out of this, because this thing will not evenly divide. That 5 would never divide 2 to the p minus r. It has to be able to divide this evenly. And when it does, it's basically d times 2 to the r. So this is really critical. All it's saying is that whatever number we have, that is the so-called the d that we want to convert to a binary fraction, be divisible when multiplied by 10 to the r by a power of 5. Anything else would not make this d a proper number. It will just not be a proper fraction to be representable. It's impossible to represent d in binary unless it's actually divisible by some power of 5, and that some power is 5 to the r. So let's look at an example here. Maybe that'll explain things. When you look at 0.125, this can be represented in exactly 3 bits, since 0.125 times 8 is equal to 1, and that's an integer. And of course r itself is equal to 3, and that's less than or equal to p. And more importantly, the numbers that we could really represent in 3 bits will be just multiples of this number, 0.125. They will be 0.125, 0.25, which is 2 times that, 3 times, 4 times, 5 times, 6 times, 7 times. And every one of them is divisible by 5 to the 3, because this is really the first one. This is, of course, still divisible by 5 to the 3. This is also the same way. And every one of them, if you notice, evenly divisible by, I would say, a third power of 5. Or you can even think of that as maybe as a fraction, 0.125, and that every one of them is divisible by that number. But you can even say that's divisible by just 125, which is like third power of 5. And when you make this p equal to 4, only the integral powers of this number now, which is the fourth power of 5, basically divided by 10 to the 4, is what this, how you get this, is only the multiples of this number would be divisible by or only the multiple of this particular sort of like fraction will be representable in 4-bit mantises. Again, you will notice that 5 to the 4 only divides just 10 to the 4 times 0.0625, which is 625, which is what 5 to the 4 is. And of course that, and then all the integral multiples of this will be divisible by 5 to the 4, which is basically like taking the fraction and making it an integer, and then keep multiplying that as long as you can until you expire yourself with, all the multiples of this number that you can represent with 4 bits, which will run up to obviously 15 in this case. So there are clearly, as it says, the 15 such proper fractions, not counting the 0. And as I said, they are all divisible by 5 to the 4, which is this magical number that we talked about, 5 to the r. R was in this first example equal to 3. In second example, r is equal to 4. Now, there's one other, and this is something we talked about already. There's one other issue that we have to deal with, and it's the notion of truncation and rounding. And when we talk about numbers with a certain number of bits, like p bits, and take an arbitrary number m, we could sort of think of any number between m and, let's say, a number a little less than m, which would be this number, just the next number to it, because this is the smallest we can write. Any number between, let's just say, m and this number, or this number and m, is not representable by, in this notation, in this p-bit mantissa. So it has to be either moved to m or to m minus 1 over 2 to the p. And so we have to decide. And in order to decide this, we have to look at the representation. So here's this number m, and this number m minus 1 over 2 to the p, which is the one that is closest to m. And there is some other number which is right in the middle. This is clearly not representable in p bits because it's a number between m and the one that is just smaller than that, and there's nothing else that can be between them. So these numbers in here, none of them are representable. And the one in the middle is how we can tell whether the number that we're interested in approximating should go to this number or to this number. So if that number m sub u is actually between half point between these two numbers and the point on the left, like in this first half, then it must go to here. If it's in this half, it must go to here, this mu. And these formulas here just basically express that. So effectively what this is saying, that if mu minus this quantity, which is this quantity here, is less than m minus mu, which is this quantity, that means this number is closer to this, then it must be mapped to this number, which what this statement is saying. This is the same statement. It's just saying that this mu is between here and here. That's what this inequality is saying. If you just look at it, this is the upper bound, this is the lower bound. And so you're just simply saying, if it's in here, just map it to here. Otherwise, map it to here, which is the other case. So this can be actually mechanized in a way that is somewhat more obvious. But let's take a look at this example first of all. Let's say that we take an 8-bit mantissa, and we take a fraction, which is 12 over 16, which is how you write in binary here, 3/4. Now let's say that we want to consider some number between this number and a number that is just this number that is 12 over 16, and the number that is just before that, which is obviously 1 over 56, subtracted this from, subtract this 1 over 2 to the 56 from 12 over 16, that's where that lower bound would be. There's nothing between these two numbers in 8 bits. Now, so let's just take a number, such a number, like, something that we subtract, something that we add to the lower bound, that will actually still be less than 12 over 16. And that would be the case if you just add to it 3 over 1024, because 4 over 1024 would have made this 0. That means 3 over 1024 would still give you a difference here, which will keep it be less than 0, which will keep it in here. A little more than this, but still less than this. So that's a number that's not representable. And this number, of course, is greater than 12 over 16 minus 1 over 512, which is really the midpoint between 12 over 16 minus 2 to the 56 and 12 over 16. This is the midpoint. And this number is between the midpoint and 12 over 16. And therefore, our number in this case must be approximated as 12 over 16. So this is sort of like mathematically how you would figure out where to go, whether you should go down to this number or you should go to this number on the other end. In this case, it's fairly obvious that we just simply check to see if the thing was over the middle point to the right or over the middle point to the left. In this case, it turned out to be over onto the right. So this is really related to truncation and rounding. What we're doing basically is, in both cases, we're just simply ruling out the bits that are outside the available number of digits. But the manner we do this in the two cases differs. In the rounding process, we simply take into account the remaining bit being 1 or the leading bit of the remaining bits being 1 or not. And so if we were to have a p plus r bit mantissa, we look at the bit that is just past that pth bit on the right. If that's equal to 1, we ignore everything else beyond it, and we make our mantissa what it would be without those r bits, but added to it 1 over 2 to the p. And we make that bit equal to 1, basically. If that is not the case, because we're going to contain it to the only p bits, just keep in mind. If that is equal to 0, we then drop them all. We don't really pay attention to it. Now, if it's truncation, we don't really do this algebra. We simply drop all the r bits, and then we keep only p bits. So here's an example. We have a 10-bit fraction, and the 8 bits are here, and these 2 red bits are the remaining 2 bits. In other words, r is equal to 2 in this situation. So this number is what we wrote before. This is basically 12 over 16 minus 1 over 256, what this number is. And then plus 3 over 1024, which these two ones collectively represent. And we simply sort of round this to this number, which is what we concluded earlier. We said that this was closer to 12 over 16, and that's what we did here. And to do that, we looked at the bit here, the first bit in the remaining r bits, and finding that to be 1, we added that 1 to this string of bits. When we did, we got this number. So if you add 1 to this number here, like 1, 0, 0, 0, 0, 0, 1, and that's what you get here. That's how you get this number. This was rounding, basically. If we hadn't rounded it, but truncated it, we would have gotten ourselves this number without these being there. That would then have been this number, which is equal to just the number in that inner representation to the left of 12 over 16. There's nothing in between the two. This number is somewhat fictitious because it's got more bits than we can afford, and therefore actually with rounding it goes to the number that is the larger of the two, without rounding, but truncation, it goes to the number which is below just that largest number, which is in this case 12 or 16, and minus 1 over 256. So that's really the difference between rounding and truncation. And this, I think, explains the same thing, so you can go over this by yourself. And this further explains how we would deal with this if this were to be a decimal representation. Again, I will leave this out. One other thing that I want to mention is, maybe this is important, that when we think about small numbers, we have to be careful. So what this example illustrates is that in this 32-bit single precision representation IEEE 754 format, excuse me, this is a biased exponent, so that's actually equal to 13, so minus 7. This must be 2 to the 6, which this is, and this is the same 2 to the 6. So you're going to multiply whatever this mantis with a hidden bit of 1, it's 1, 1.1, with a hidden bit of 1, 1.1, and everything else, of course. And so these numbers respectively correspond to, like, this is 64 plus 32, 96. That's because 64 and then 32, which is 1/2 that times 64. That's 96. And this number would be, again, 64 plus 32 plus some more number, some other number, which is this number, which is, I think, 1,000, 2 to the 6 divided by 2,048, which is basically 64 to 2,048 must be like equal to this fraction. So here you get two numbers, and there's really nothing else between the two because of this thing that we talked about earlier, because everything else is 0, and if this were to be 0, this number would be identical to this. So this is the next number greater than this. Now, if we were to change the exponent to something smaller, and then it basically figured out that we wrote a number, maybe make it even denormalize, and write a fraction like this. Yeah, denormalize it first, so make all the exponent bits to 0, and therefore the hidden bit is 0, and then put a very small number in. For example, something as small as 0.02. And let's say that we had a loop where we wanted to add 1,000 fractions that are basically all smaller than 0.03125. And one such number would be 0.02. Now, when we did this, there's no number between 96 and this number would be closer to 96. Or even if it isn't, let's say, in fact, it will be then truncated, or if we truncated it, let's just say that we truncated it, forget about, which one is closer, then every time we made the addition, because of the truncation rule, this would have not been ever added. Because it's a number between this and this, truncation simply would take it back to this. So that truncation, done 1,000 times, would have made us lose 20. And we would have gotten a 96 instead of having 96 plus 20, which would have been 116. So this would be a significant error. And engineers have to be very, very careful not to make mistakes like this, because these kinds of errors in computations can lead to, I would say, catastrophic issues. If you're designing an airplane or you're designing a spacecraft, all those very critical missions have to be very, very carefully done when you do things like this in order to avoid any issues with obvious problems like this. So truncation, even with rounding, even if you end up going to this number, you would still have a problem, because then you would have actually overshot it. So the thing would have been to add this 0.02 1,000 times and then add the number. Not added in the shadow of 96 or 96.03, but added separately. So in other words, the rule is that you don't add big numbers with small numbers and expect to get something reasonable or sensible in floating point notation. Maybe that's what we want to take to the towards the end of this first half of the presentation as our maybe major point. That the main limitation of floating point operations would be that the large and small numbers cannot be mixed together. In the integer domain, we never had a problem like this. 2's complement floating point number system, I will probably not say too much about it, except to say that numbers are represented in 2's complement as fractions or fixed point numbers. Like here's an example. If you want to know the value of this number, the radix point in here, what you have to do is just complement the bits, which we've done over here. As you noticed, these bits have been complemented, and then you need to add to this not 1, but actually 0 points, some number of zeros followed by a 1, which is the smallest fraction that you could have. And that's how you make this notation work itself. You're not going to make it, like you're not going to add the 1 in here, but you're going to add the 1 then in there. And that means that you're going to add this fraction. That's how another way to think about this is you move the radix point to here, complement the bits, add the 1 in here, now move the radix point over there. That's the same thing that you would, that would have given you the same answer. So this is fairly straightforward, and I'm not going to say much more about this. So I'm going to end the video at this point, and when we come back for the second installment of this, I'm going to talk about addition, multiplication, and division, and subtraction, of course, in floating point. The rest that will be done in the second installment, as I said. Until then, take care.